Okay, quick tutorial on how to make a scatter plot in Excel and add a trend line, look at the R-squared value, and extract an equation of a straight line from that trend line. So let's just pretend that we want to plot these data. So we've got the toss number for how many times you're tossing a washer towards a target, and then the distance that that target is from the center. And let's make a plot where we want to see what the distance is as a function of that toss number. In other words, we could generate a hypothesis that says something like, do we get closer to the target the more times we make a toss? That's a really good use of a graphical piece of data analysis. So to make a scatter plot, we'll go to Insert, and then we'll go to Charts over here, and then choose this top one. We never want to connect our dots with lines, because lines imply we know the relationship between those dots, but we don't. That's what we're seeking to understand. We have no idea what the functional form of a relationship would look like, so we'll just plot the dots. So it's going to give us this blank document as long as you don't have anything pre-highlighted when you click that scatter. Now we'll go to the chart design tab. That should automatically open, and then click select data. That's going to prompt me to add a series. I'll click add. I don't need a name for this. I can go to X values. Remember, X values are the independent values on any plot, meaning they're the things that you're controlling. So our control here is the toss number, because we're the one choosing to toss that ring. And then the functional aspect is the Y value. That's the thing that changes as a function of toss number, or at least we're investigating that. In that case, that would be the distance from the center. So I'll click that and then choose OK, and then choose OK. I could add another series here if I say wanted to then look at what the dominant hand was, and then I would add another series and select the two. But in this case, I just have a single series on one graph. I'll click OK, and there's a few things that I'm going to do that's in line with best practice of these sorts of plots. So over here, this plus sign gives me lots of options for how I want to format this thing. It's never customary to include a title in a graph in science. Much to maybe your intuition, never include this. And so we'll always delete this. Graphs always have captions underneath of them anytime they're published, whereas tables always have a title at the top. And so Excel will default to add a title. Always remove it. That's not good practice. I like to remove the grid lines because I think that it cleans up the plot. Of course, this graph is 100% meaningless to anybody unless there are axes with defined unit. So we'll click Axis Titles, and you'll see now I can choose a title to enter here. And so remember, this is distance, and this is in units centimeters, so always include units here. And this would be toss number, which doesn't have a unit because it's just an integer value. And so this is a really nice representation of the data that maybe we didn't see when it was simply in tabular form like this. But now we can start to say, oh yeah, actually, as the toss number increased, I started to decrease my distance from the center. That's great. I wonder what the actual relationship between the Y variable and the X variable is. Well, that in this case, this looks like a linear relationship. And so to evaluate that, I could just fit a straight line to this. The line will be regressed through this, which is a mathematical process called line of best fit, which we won't cover how that happens here, but it's essentially going to measure the distance between every single point here and find a line that best minimizes the overall distance from the spread in the data. And I can do that by clicking again on the Chart Elements tab here and then going down to Legend. And you'll see the line gets added, but what I want is to know what the equation of that line is, so I'll choose more options. And notice I can fit this a variety of different functions. In this class, we'll almost always deal with linear functions. And actually, that's true for most science, because it's always better if we can rearrange our variables so that they're in a linear relationship to each other. It's always easier to fit a straight line than it is a polynomial or an exponential. Now down at the bottom here, I want to choose these last two boxes. I want to see what the equation is for the line that I've chosen, and I want to set the R-squared value. And I'm going to click here and just drag this so that it's easier to see. And then maybe I will increase the size so that we can read this a little bit better. So what this is telling me, there are two different things. And so we have the r-squared value. First, the r-squared value is a measure of how well the points or the data fit that line that was added as the trend line. A value of 1 is perfect, 1.0. That means that the points will lie exactly on the line, no deviation. In other words, the way you can think about the r-squared value, sometimes called the correlation coefficient, is that right now, this trend line, which is a single line in space defined by this y equals mx plus b equation, it defines about 93% of the data itself. That means about 7 or 8% of it lies sort of outside this general trend. But otherwise, this is a quite striking fit. The other thing that's included here is the expression y equals mx plus b, where this is our y variable, distance, that's y, and x is our toss number. And so now we have a relationship between any arbitrary toss number. Say we wanted to extrapolate this and say, what would happen if we continued to toss, say, the 25th value? Now we could input 25 for x, solve for y, and we would end up with some anticipated value of distance. We will use trend lines a lot in general chemistry and in other more advanced chemistry classes because this allows us to extract a quantitative relationship between variables. Just as a quick additional aside, what I find to be extremely valuable is not necessarily, if say I wanted to do the example where I wanted to predict what the distance would be for a future toss number. Rather than transcribing these values from the equation or copying them into a formula, what I could do was build my own formula here. And so this 78.108, that's the slope, that's m, and this is the interceptor, b. And so I can compute those directly here. I could say slope, and then there's actually a formula called equals slope, go figure, and it's telling me to input the known y's followed by a comma and then known x's. So my y's for these data were the distance, so I'll put a comma in there and then choose toss number, close this, and press enter, and notice that the slope here is now exactly same value here, but there's no transcription error because that's computed directly from the formula. Similarly, I'll type b for my intercept equals intuitively here, intercept, and then choose again the same series of data, y's first, comma, then the x's. And now let's pretend that I would want to compute y for an x equal to 25. So let's just say x here is 25. What is y? Well, now we can just do a solution here where y is equal to that slope times x plus this value. So I would say parentheses just to be safe here. You didn't have to do this, but I will take that value, I will multiply it by my x value, and then I will add on my b value, and that is predicting that actually I would go negative, which of course is not a real value here, but you get the point here. Because we were approaching 0, this line naturally starts to intersect down here, and we could have predicted that. Let's say, for instance, we wanted to predict 21. That would give us a realistic number because the intercept here is probably somewhere around 22. Let's see, 22, and that's negative. So between 21 and 22 tosses, we start to have perfect accuracy. That's what this line would predict.